So on this slide, we have a terminology review. We've gone through all of these before. However, it's good to review through them one more time so that you know what's going on. So look through this. If there's any of these that don't make sense, look them up. Look back to the previous slides. Look at the symbols for them. And as for right now, kind of understand each of these definitions so that you have some kind of understanding of them. If you don't, definitely come to office hours and we can chat and go through this because it's important early on to understand. So, planar circuits. So, planar circuits are something that we strive for. We strive to be able to draw circuits in 2D without branches crossing each other. So, remember if we look back at the signal and we have that little bump up, which you see in picture A there in the middle, it's not a node, and it kind of says that this wire doesn't cross this. It's okay, but as much as we can possibly do, we try to refrain from using that because technically, if you don't draw it right or if you draw it too small or something, somebody could mistake it later on as a node there, and that would be very bad. So whenever possible, we try to pull those away so that we redraw it, so that's a lot easier for us to see. And there's a couple ways to practice this. There's not really a good way to be able to explain this except by doing it a few times. And actually, there's a fun little game that I'll show you that can help early on with creating these planar circuits. So this is just a fun thing. This is a fun little puzzle game I found actually on Android. It's on iTunes as well. A couple years ago, and I just started playing it out at one of the at a bus stop, I think. I was waiting for the 32 or something. Anyway, this game's called Tangled. It is an awesome way to kind of practice how to change things to planar circuits. And again, it's a game, it's a puzzle game. It's not directly electrical engineering, but it does actually really help. So I'm not saying you should spend your entire week doing this, but I'm saying if it's the choice between this and Tetris, we're going to go with Tangle because at least you can get a little something out of it while you're standing there at the bus. So look this up, put it on your smartphone, play it a little bit this week. It's a really fun game. Tell me what you think, actually. So maybe you've heard this already a couple of times, but electricity has a lot of parallels with what essentially we call it the water analogy, or the flow rate of water through a tube, which is kind of mass over time. You can think of the same way the flow rate of currents through a tube, which is charge over time. So we're going to go through this analogy because for a lot of mechanical minds, it makes it a lot easier to understand some of the concepts we're trying to do in electrical engineering. So a little bit more with the circuits and water analogy. Voltage has some equivalence to pressure. So if you think of a giant water tank high above the ground and the pipe coming from it, you can kind of think of that as a good analogy to voltage. So you have a battery which has a lot of voltage stored up inside of it, and that's going to push the electrons out through the wire. So the same way that a giant tank of water at the top of a pipe is going to push that water down through the pipe. We have current is the same as flow. That's a very good analogy, actually. So current equals current. Water current equals electrical current. You kind of think of them as the same. Water current, you have an amount of water or mass pushing through a pipe hole at at any given point in time, trying to flow through that pipe. Same with like electrical current. You have a bunch of electrons or electrical current trying to push their way through a wire at any given time. Resistance is the same in both of those, so if you have resistance in a pipe, maybe that pipe gets a little narrower in the diameter decreases, and that's the same way you can think of it in an electrical circuit. The resistance of that electrical circuit, as it increases, less and less current gets, less and less electrons get through it. So that's another way to think of that one. So here's a complex one, though. Resistance is impedance, but impedance is not resistance. So whenever we're working with DC circuits, it's pretty straightforward, as the analogy goes. However, when we're working with alternating currents, since the current is changing through time, we have some different technical terms like impedance. And for a DC current, a DC circuit, impedance is the same as resistance. It's essentially the magnitude, but In an AC current, impedance contains a magnitude and a phase, which makes it more complex. So again, we're going to go through alternating current circuits in a bit, but just keep in your mind that for impedance, the water analogy, does not always work. It's a little more complex than that. There's other electrical impedances as well, such as inductors or capacitors, and essentially they all impede the way that power flows through the circuit. So with that being said, they have different properties that we're going to look at later, which become very useful as well. So here we have a little bit more on mass flow versus the electric current. So the water flow analogy versus the electric current analogy. So on the left we have blue, which is showing mass flow or water flowing. There is a giant reservoir at the top, and that water is trying to flow through that blue arrow line to get to the bottom. So if we have a change in potential energy, we have mgh1 minus mgh2. So essentially that's saying if we take out the mg, the change in the height is creating our pressure. And why does the change in height create pressure? Because we're in a gravitational field. And that change in the gravity between the two is essentially creating a pressure to pull it through. So think, if you had no gravity, zero gravity whatsoever, water is not going to flow from tank 1 to tank 2, which makes sense. So if you go up in space in a zero gravity environment, you always have to have essentially a pump to be able to pull liquid from one place to another. Whether you're cooling or whether it's a toilet or something that you're using on the International Space Station, you have to have pumps to move that all the time because there's no gravity to pull it down. So with that being said, water flow, or the flow rate, is mass over time. So you're thinking of the total mass, the kilograms of water flowing through that pipe per second. And that's going to give you your flow. Now, in an electric field, we're looking at how charge flows through that cable in a given time. So we have the change, or delta PE, the change in the potential energy, equals QED1 minus QED0. And essentially what that's saying, if we pull the QEs out, is the change in voltage. The change in voltage due to the change in the electric field is what's pulling it down. So there's a higher electric field at one side and a lower field at the other, and that's pushing it through. That's pushing your charge through. So you can think of this kind of current as charge that's moving through the pipe over a given time. So how many coulombs are going through that wire per second? And that helps us get electrical current. So with electrical circuits, we're going to look at closed paths. So on the right, you see this very simple diagram again of a battery with a light bulb and then the return to the battery. And again, I put closed there because if you have a break, electricity can't flow. Charge can't flow through a wire if there's a gap in it, unless you get really, really close, and then essentially that charge can break through the resistance in between there and you get a little spark or a little shock. But that's a little bit beyond what we're doing right now. Essentially, though, we're saying for an electrical circuit, we can describe it with three individual parts: voltage, current, and resistance. And additionally, you could do capacitance and inductance, but those are special cases. For most circuits, for a very basic understanding, the three in red are the most important. So voltage, V, which is the unit we use as volts. Current, we use the symbol I, which is in amperes. Resistance, R, the unit ohms. Sometimes we use a weird little symbol, which I'll show you in a couple slides from now, to dedicate ohms and what that means and what that looks like, instead of writing ohms out every single time. And then capacitance, the unit of measure is farads. Inductance, the unit of measure is henries, which we use L to designate that. So capacitance, C, that makes sense. Inductance, L. Why didn't we use I for inductance? Because we already used I for current, and so we need another letter, so we used L for inductance. So here we have another description of the water flow rate versus electric current. On the left, we have a picture showing a pump giving a volume flow rate. That pump is pushing whatever liquid, we're going to call it water here, through these tubes at a very set flow rate. So here we're going to say some centimeters cubed per second. As that water flows around in the direction of the arrows, it's going to pass through a thin area on that, which is, we're going to call it, that's the resistance. So if you think of this in action, like if you're drinking Coca-Cola and you have a straw in there and you're drinking it, it's pretty easy to pull the Coke through the straw. However, if you pinch on that straw really hard, it gets harder and harder to pull the Coke through the straw. The resistance increases, and therefore you have to put more energy on that pump to pull it through. So that's essentially what we're trying to do here with resistance and the volume flow rate. We do the same kind of thing, the same analogy holds exactly for electric current. If we have 12 volts, essentially that 12 volts is pushing the voltage through. That's giving us a charge flow rate instead of a volume flow rate. And that charge flow rate we call current, I. And current is coulombs per second. So it's essentially charge per second, or amperes is the unit that we use. So how many amps are we pushing through? And as that resistor increases, as that amount increases, it gets more and more difficult to push that current through that part of the wire. So that's the same analogy between the two. As we go, we're going to go through a couple more analogies and a couple more derivations to be able to show how current, voltage, and resistance are related. So in this side, we're going to look at charge and current. So charge can either be positive or negative. A positive charge is called a proton, a negative charge is called an electron. And these are the most fundamental units of charge. So in physics, we've looked at a couple of times when solving problems between protons and electrons. So a proton repels a proton, an electron repels an electron. However, a proton attracts an electron. So opposites attract. In this slide also, we're going to look at the charge on a single electron. So we use the letter E to look at the charge of a single electron, and that is 1.6 times 10 to the minus 19 coulombs, or C. So the charge of a single electron is very, very small. So how do we get larger charges? How do we get 1 coulomb or 2 coulombs? We do that by sending many, many electrons through a wire. So a rule that we have is the conservation of charge, and I mean, think of positive or negative charge as essentially energy. The conservation of charge means that the net charge in a closed region is conserved. So what that means is essentially the charge is not going to be going magic places. It stays within the system. So in this simple circuit diagram we have below, the charges are going to move around within the wires. They're never going to leave the wires for now. Charges are of the same polarity repel, and charges of the opposite attract, which we just went through. So in this small diagram here, we're going to look at an electron traveling through the wire. And if you look at the diagram, it's not actually done wrong. You might see the V positive and the V negative, and the E minus is traveling actually in, it looks like, the opposite direction of the positive. And there's actually a silly reason for this, but that is the correct way of doing it. So just remember in the back of your mind that electrons are actually traveling the opposite direction as the positive voltage and negative voltage. And we're going to study why in the next slide. So the reason that there's some confusion is actually coming back to Benjamin Franklin. So when Benjamin Franklin was conducting his original studies of electricity, we didn't know very much about particles, particle physics, or electricity in general. So Benjamin Franklin observed what we now know as protons traveling. And protons are the exact opposite, like we talked of electrons. So whenever we look at that previous slide or any drawings of circuits and we see the arrows pointing the direction of the current, we're actually pointing there in the direction of the protons and not the electrons. Why does it matter? So for all mathematical purposes, it doesn't. We go with it. Even though it's kind of a mistake, as long as we're presuming all of the current is always going to flow in that direction with the protons coming out, that's what we know. But in the back of our heads, now that we have analyzed this a little bit more and we know a little bit more about particle physics, we actually know that the circuit is working in reverse and that the electrons are flowing in the opposite direction of the lines that we draw of the currents. So this is really confusing. For mathematical purposes, continue doing it how we've been doing it and how I'm going to teach you how to do it. But in the back of your mind, just know that the electrons are actually moving backwards through the circuit. If you need to do this, talk about this more, we come visit office hours and we'll sit and we'll chat and I'll explain it to you because it is a little confusing right here. It's just a good fact to know, actually. If you want to learn more, also you can use the link I provided below, or you can just Google flow of electrons or direction of electrons, direction of protons, and that'll give you some descriptions as well. There's a couple good YouTubes on it. So, to the best approximation you can do, how long would it take for an electron to enter one side of a 60-meter copper wire, let's say the red one in the picture, travel through the entire wire, and for that same electron to come out the other side of the red wire? Would it take the speed of light? Would it take 1 nanosecond, 1 millisecond, a second, a week, a year, or the electron never leaves the wire? So in order to answer that question, we need to know something about electron drift theory. So electron drift theory is essentially stating how long or how fast it takes for an electron to drift through a wire, because it's not immediate. So sorry to say, if you said speed of light, that is the only wrong answer that exists there. We'll go through that again in a minute. But electrons are going to move in the opposite direction to the arrow and eye of the current direction we've drawn. Because remember, the current direction we've drawn is Ben Franklin's positive charge direction. The electrons are actually moving opposite of that because they're attracting to that positive charge. So the electrons, which again are the major charge carriers in electrical engineering and in the world, are going to flow in the direction opposite to the current direction that we draw on the paper. So each electron is going to flow in a very random, scattered pattern, but it's going to have a slight directionality because it's being pulled in the direction of the protons in the current direction. So with this being said, though, the speed at which they move is dependent on multiple things. It's dependent on the cross-section, the area. It's dependent on how much voltage is applied. It's dependent on what type of wire you're using. Are you using copper wire, aluminum wire, carbon fiber? All of these are going to impact how fast the electron flows through the wire. So for a typical wire, though, we're looking at like a response time of 0.2 microseconds and an actual travel time through a 60-meter wire of normal size with 8 volts propelling it at about 10 days. The more important thing to remember this, though, is current flow is defined from the direction of positive charge movements. So that's the exact opposite of the electrons. The electron movement is the predominant charge carrier, and they're going to move in the opposite direction. So to get back to our question again, we're going to look at, in the best approximation, how long does it take for an electron to enter one side of the 60-meter copper wire? So if you had said a speed of light, that's the only incorrect answer that we have. So if we're going to go through, if it takes 1 nanosecond, that's extremely fast. That means, one, that you don't have much resistance to. There's a lot of charge carriers, a lot of electrons for it to move with. And that's also going to mean you have a huge voltage potential behind it. So you're going to be in the many, very, very high voltage. It's going to drop down. That voltage is going to drop down at the millisecond range and the second range. If you're getting to the weak range, you're probably getting around like 8 volts instead of maybe many thousands of volts. If you're getting down to the 1 year range, maybe you're on like a thousandth of a volt, or getting smaller than that. It never leaves the wire is possible if, you never plug it in. If there's never anything creating a voltage at one end of it and propelling them through, the electrons just kind of stick around there. And technically, the electrons even could exchange with the electrons in the plastic, although that's not as likely, or exchange with electrons in the air. So it never leaves the wire. Extremely far-fetched, but possibly could happen.